I want to finish up section 1.1, just an introduction to systems of linear equations. We gave the three basic model types for a solution. That is that a system could have a unique solution, the system could have infinitely many solutions, or a system could have no solution. So we just looked at that in just very elementary format. Make note here that solutions for any square, and what we mean by a square system is that the number of equations equals the number of the system is homogeneous. Each equation is set to equal to 0. So for any squared homogeneous system, the solution is always the trivial solution, where x sub 1 equal to 0, x sub 2 equal to 0, x sub 3 equal to 0, based on how many variables you have. We looked at how you can go from a system notation to a matrix. So if the system here is written in terms of what we would just say, just the straightforward system notation, you can transfer that to a matrix, and then vice versa. You can go from a matrix to a system. And I think this is where we stopped. And here are examples of non-homogeneous linear systems. Non-homogeneous being that these numbers here are not 0. And so now, of the three types of solutions, the no solution, unique solution, or the infinitely many solutions, if the system has infinitely many solutions, you have to be able to find that solution set. That idea will follow us for the duration of this course. We start off in a very simple way, but we'll build on it, and it explodes later on into other concepts that basically mean the same thing, that I have infinitely many solution set. So here, these examples, in each part, find the solution set of a linear system by using parameters as necessary. So in other words, if you have, this is one equation, but I have three unknowns. So you may say, well, it's impossible to solve that guy. Well, technically so. Here we say that we have infinitely many solutions, because if I have one equation and three unknowns, then you're going to say 3 minus 1, that is 3 unknowns minus the one idea of one equation. That leaves you with 2 variables that are said to be floating, or that can be anything. In other words, if you know what y and z are, you can solve for x, right? So, or if you know what x and z, what they are, you can solve for y. So it's like, I need to have 2 of these guys to be able to solve for the third one. So the 2 guys that you need, we call those floating parameters. They could be infinite. Whatever selection that they are is infinite in the selection. So if that be the case, then we're going to go ahead and claim, doesn't matter what variables here you claim to be the parameter or the floating variable. I'm going to say let y and z be the parameters. And we just give them a name. Now why is that important? Well, it's very important in mathematics, and for those who are interested in computer science and computer programming, assigning something of value to computer programming is most essential. That is that in the beginning of the program, you have the definitions, and then you have the assignments, that I'm assigning this term, this variable. So within the computer frame, it has a cell, and so in that cell, we have a marker that this cell is called X, but then in X, I put a number, right? And so this assignment is most important, and I should say it's also divine, because the name is most significant of the person. Does the name of the person go with the person? And so here in mathematics, we have what I believe divine intervention. So let's let y equal to, let's say, some term. So let y equal to, let's say, s. And here s is any real number. And then let's let z equal to t, where t is any real number. So if s is any real number and if t is any real number, then you get the idea that that the solution then for x could be infinite. And so for all values, x, y, and z, we have infinite choice. So here we get 3x is equal to 7 plus 5s minus 4t. Now x is 7 plus 5s minus 4t all over 3. So the solution set, the infinite solution set, is the choice for x, which x depends on the y and the z. So here x is 7 plus 5s minus 4t all over 3, comma, and you could have written it as 7/3 plus 5/3 s minus 4/3 t. It doesn't matter. And then here the choice for y is s, and then the choice for z is t. So the same idea here, part B, you have 4 unknowns, 1 equation. So that means that 3 of these variables would have to be floating parameters. So let x2 equal to, let's say, a. A is any real number. X sub 3, let's call that b, some real number, and then x sub 4 equal to c, again, another real number. So we just isolate the x sub 1, so negative 8x sub 1 is equal to 1 minus 2a plus 5b minus 6c. And so x sub 1 is negative 1/8 minus, here, plus 1 over 4a minus 5 over 8b plus 3/4 c. And so our solution set would be the choice for x sub 1, negative 1/8 plus 1/4 a minus 5 over 8b plus 3/4 c, comma, x sub 2 is a, comma, x sub 3 is b, comma, x sub 4 is c. Let me cover this small last part here in this section that I've added, and then we'll go online and look at a few problems from section 1.1. Okay. In terms of manipulating the system, here the system or the matrix, we only have 3 operations, 3 things that we can do that we're allowed to do in terms of manipulating the system to try to solve for it. Well, I'm solving for what? To see if it has the unique solution, to see if it has infinitely many solutions, or to see if it has no solution. So within my parameters in terms of what I can do, there are 3 things. I can interchange the rows, and you know, for the matrix we talk about a row, and then for the system we talk about the equation. So I can interchange the equation. So if you have equation 1, equation 2, equation 3, you can write equation 1 where equation 3 is, and then write equation 3 where equation 1 is. So you can interchange those equations. It doesn't offset the solution. The solution still stays whatever it is. You can multiply a row by a non-zero constant. Typically, you want to try to cancel out a variable to get a zero somewhere. That does not mean that you can just multiply that row or that equation by zero. That's what the second grader would say. I know how to get rid of it. Just multiply by zero, right? Here, we multiply any row by a non-zero constant. And then the third operation that we can do is that you can add a multiple of one row to another row. Right? So those are only the three things that we can do. But with that, you can do so much. Note, of the three solution types for a system, the unique solution, that is that I get a solution, is consistent and independent. The no solution is said to be inconsistent because consistency is just based on the idea of a unique solution, or I get a solution. I get something where the graphs cross at a point or they cross at a plane, if we're talking about vectors. So for the unique, the no solution, or the infinitely many solution, if it's infinitely many, you have to solve for that solution set. Kind of the idea of what I just got through doing with those previous two examples. So what I'm going to do here is give an example of a system, and I'm already telling you that that the system has infinitely many solutions. Well, we're going to use parameters, parametric equations to describe the solution set. Let me show you that. And what I do is when I solve a system, I just like to go ahead and interpret it as a matrix and then just go from there. So, so my goal here is not to show you how to solve the system, which you may know how already. I'll show you that in section 1.2. My goal here is to show you that if I do have a system and if it has infinitely many solutions, how do you write that solution for that particular system? Okay, so I'll go over it now. We'll run across some more problems in 1.2, same setup, but you'll know what to do. So the meat of what I'm going to do to get to the solution, just watch. But how I write the solution, that's what I want to capture right now. So I'm going to write this system as a matrix. So, so what I'm going to do here is to, where I have this 1, I'm going to get a 0 here where that 3 is, and then use that 1 there to get a 0 here down below. That's a 3, I think. Yes, negative 3. All right. Well, let me just deal with that first. So here we're going to say row 1 plus row 3. That always will give us a new row 3. I'll leave row 2 just the way it is for right now. So I can use this one, or this elimination method, to add the terms in row 1 to row 3. Well, it gives 0, 0, 0, 0. Everything cancels out. Now, when you have a system and when the entire row cancels out, including this number over here where I get a 0 there, then that's setting you up for infinitely many solutions. Now, what I'm going to do is try to simplify it a little bit further. For me, is to use this one, that we call that a leading one. If the first term in a row is a 1, we call that the leading one. It's a leading one because you can take one, multiply it by any number to cancel out another number within that particular column. So I'm going to use this one to get rid of this 3 right below it. So I'm just going to multiply negative 3 times row 1 plus row 2. Again, I'm going to go through all these steps in section 1.2. So negative 3 times row 1 plus row 2 gives us a new row 2. So this is a 0 here. So negative 3 times 3 is negative 3 plus, well, that's negative 9 plus 9 is 0. Then I get negative 3 times negative 1 is 3 minus 1. We get a 2. And then here we get 12 minus 12, 0. This is 0, 0, 0, and 0. Well, I think we can stop there. So if I interpret what I have, this implies that this is x sub 1 plus 3x sub 2 minus x sub 3 is equal to negative 4. And then the second row says this is 2 times x sub 3 is equal to 0. So automatically I can go ahead and get x sub 3. What's x sub 3? It's 0, right? So here, this implies that x sub 3 is 0. So if x sub 3 is 0, then all I have is x sub 1 plus 3x sub 2 minus 0, right, is equal to negative 4. That is to say, this is x sub 1 plus 3x sub 2 is equal to negative 4. Right. So this is one equation, but I have two unknowns, right? X sub 1 plus 3x sub 2 is equal to negative 4. So what I'm going to do is let x sub 2 be the floating parameter, just be the free variable. So x sub 2, we'll say let it equal to, let's say, s. Yeah, s is fine. Doesn't matter. So let x sub 2 equal to s. Then that means that x sub 1 is equal to negative 4 minus 3s. So therefore, the solution set is x sub 1 is negative 4 minus 3s, x sub 2 is s, and x sub 3 is 0. Now, if you notice, in terms of how we just got through writing the solution set, is very similar. It's the same thing that we did up here, right? With that particular problem. Same idea. Right. Now, let's take a couple of these problems, then we'll look online. Here, find one, two. I don't know how it came off. So here, find a single elementary row operation that will create a 1, we call that a leading 1, in the upper left corner of the given augmented matrix. What do we mean by an augmented matrix? Remember we said there was a difference between the coefficient. The furthest column, right? Exactly. So that furthest column over there doesn't have any variables associated with it, right? Good. And so it says find a single elementary row operation that will create a 1 in the upper left corner of the given augmented matrix and will not create any fractions in its first row. So it says find a single elementary row operation. How many row operations do we have? 3, right? And they are, everybody like the choir. The first one, okay, you can interchange equations, right? Second one, doesn't have to be in that whatever order. Right? What's the second thing we can do with equations or systems or matrices? You can multiply a row by a non-zero constant. Yes. What's the third thing? You can add a multiple of one row to another row. Yes? Right? Correct? Okay. Very good. So you want to get a 1 where this -3 is. A couple ways you can do it. It looks like from the instructions they want you just to do one thing to get it. You know, some would probably say maybe 2 things to get it. Well, you can, if you add row 2 to row 1, you end up with a -1 there, right? So then what we'll do is say negative times row 2 minus row 1. Right? Add a multiple of one row to another row. So here it says find a single row elementary row operation, which are they saying just to find one elementary row operation and get that 1 there, or can you use 2 elementary row operations? Well, it could be ambiguous, right? Doesn't matter with me. So let's say, can I do 2 of them? Will that be okay? So you can actually just see it. So I'm going to say row 2 plus row 1. That gives us a new row 1. So this 2 minus 3 is -1. -3 minus 1 is -4. 3 plus 2, 5. And then 6 there. Just rewrite rows 2 and 3. Right? And then now, so what I've done here was we've added a multiple of one row to another row. So then the second elementary row operation that I would do to get a 1 here is to multiply row 1 by a -1. I can multiply a row by a non-zero constant. So we just say negative times row 1. And I could have done row, I think negative times row 2 plus negative row 1, but that's just too much for my simple head. So this is 1, 4, -5, -6. Just rewrite the other rows. Okay. All right. Now this is number 2. Okay. So how can we get a leading 1 here where that 0 is? What should we do? And that's definitely just 1. Yes, sir. Yes, sir. Interchange rows 1 and 3, right? So we'll say row 3 is swapped out with row 1. It's augmented, so I can draw that line there. Yes, yep. 1 plus 0 is 1. Yes, sir. So, you know, there's several ways you can get at getting those leading 1s. Then after that, the goal would be to get zeros elsewhere in that particular column. And we'll cover that in section 1.2. All right? So I think it's very straightforward thereafter. How would you get a leading 1 where that 2 is? I think the instruction said without leaving fractions, right? Yes, sir. Divide row 1 by 2. Or uh, we would say multiply row 1 by 1/2. Right? Same thing. Okay? Very good. Very good. Now, on your smartphone, boy, I tell you, this technology is cool. On your smartphone, I want you to go ahead and pull up Wiley Plus, and let's go to the exercise for section 1.1. So if you have your iPhone or Droid phone, or if you have your iPad or some tablet, you should be able to call that up. Let me put up here the website. See if I can pause this for a moment.